Welcome to my channel, Innova World.
Hey guys, once again welcome back to my channel. I'm here to help you guys with my best subject knowledge and ideas with you. This tutorial will be highly effective for aeronautical and mechanical engineering students, especially those who are preparing for competitive examination. Today my topic is compressible flow part 2. If you want to know more about a compressible part 1, the link is in the description below. In the description box you can go and check there, and if you have further inquiry or requested video, you can drop down to my mail to 9489224114ash@gmail.com. So here are a few textbooks which is recommendable for understanding the concept of compressible flow. So here I will bring out some few topics which I will cover in this section, that is isentropic flow, area pressure velocity relation, flow properties in subsonic and supersonic flow, isentropic flow through nozzle, and shock behavior in nozzle, and few MCQ questions which is for competitive exam. Isentropic flow. So what is meant by isentropic flow? It is a combination of adiabatic and the reversible process. So when the adiabatic and the reversible process comes together or along, we call as an isentropic process, and that process, what is a thing we consider, that is a change in entropy is constant across the process. And for example, we can consider a venturimeter or a rocket propulsion system. Now I will come directly to the effect of change in area on a pressure and a volume. First we will see, we have considered two equations. This is a momentum equation and this is a mass equation, or we can say a continuity equation. So to find out this, we need two major equations, or you can rather say that when you assuming or predicting any area pressure velocity relation, you need to consider, if you are analyzing in software, you have to predict two equations, that is a continuity and the second one is a momentum. Here we are not considering anything with the energy equation. So from here, this momentum equation, we are forming this from Euler, we are getting this this formation. Okay. Now next what happened, from the continuity equation we gathered this is a continuity equation for an compressible flow. Don't get confused with the incompressible flow. Here we are finding for the compressible flow. Now from here we keep the dA by A in one side and the other term in the other side. So minus dV by V minus d rho by rho. So from here what we are going to do is, here you see, here also we have minus dV by V. So let me substitute, instead of minus dV by V, this dP by rho V square in this term. So we get at this equation. Now we substitute here. Now after that, what is the next process? We got this. From here, by rewriting, take that dP by rho V square common. We take that common and what we get as 1 minus V square by dP by d rho. Now recalling the speed of sound formula or equation, what is that? That is dP by d rho equals to dou P by dou S of isentropic process equals to C square. Okay, or you can also say as A square, anything is okay with it. So now instead of dP by d rho, you are going to replace a dou P by dou S isentropic, that is C squared or C square. So in place of dP by d rho, you are going to replace as C square. See here, we are replacing there. Now again recalling, what is the formula for Mach number? Mach number is nothing but the V by C or V by A. So in place of V square by C square, what we can write, that is 1 minus M square. You have to remember this formula, it's very important. Let's come to the next step. After we achieve this, what we get at, now again we get this, or we can rewrite from this equation to here. Now what we are again recalling this equation, that is a end of momentum equation. From here we know that minus dB by V equals to dP by rho V square. So instead of dP by rho V square, what we are going to substitute? We are going to substitute that minus dV by V. If you do that, we get this. Or from here we can also derive like dA by A equals to dP by rho V square 1 minus MA square. So from this relation we come to this conclusion that if according to the nature of a nozzle or a nature of a speed, how by changing the area, how it is gonna affect with the pressure and velocity. So first keep in mind that pressure and velocity are inversely proportional. If pressure increases, velocity has to go down. Okay, so what I said, if pressure increases, the velocity will go down. If velocity increases, the pressure will decrease. That is our fundamental concept, that is the pressure and the velocity are inversely proportional. So first see the first formula here. So from the previous equation we can write that dA by A equals to minus dV by V, open the bracket, 1 minus MA square. So this can also be written like this, like dA by A equals to dV by V into MA square minus 1. So let's consider this formula, focus on this formula. So what they say that just consider a subsonic flow. What is mean by subsonic flow? When the Mach number is less than 1, you can see in the figure it has already written that is MA is less than 1. So when you substitute that M1 is less than 1, what you get in this formula? Here something less than 1, just consider the Mach number is, just for example, consider the Mach number is 0.8. So if you square that 0.8 minus 1, what you get, square of that 0.64, you will get it. Okay. So that's minus 64, the value which you get is, it will be getting in negative. So what you will get is the dA by A equals to minus of dV of V, some terms negative. So that indicates that at the end, if that means they are negative to each other, that is the velocity and the area are negative to each other. That means that if area increases, the velocity will decrease. Did you got the point? See this structure, this is called as a convergent construction or convergent section. So what happens? Convergent section, gradually what happens? The area decreases. So when we are considering a subsonic flow or subsonic Mach number, so what happens across a region, when the area decreases, the velocity has to increase according to this expression. See the next one here, gradually here in the next, what happens? Gradually the area increases compared to this region. The area compared to this region, here the area increases. So I said here for a subsonic they react different in nature. So that is, if area is increasing, that means what will happen? Velocity will decrease. See what happens? If velocity decreases, what is going to happen? Pressure will increase. So pressure, temperature, density, they are proportional to each other. So like how you have to figure it out, and the velocity and the Mach number is proportional, because what you know, the as per the definition of Mach number is equals to V by A or V by C. So I hope your subsonic zone is clear. Now come to the supersonic flow. Now what is meant by supersonic flow? When the Mach number is greater than 1. So now using the same formula, you apply the value, the Mach number, consider the Mach number is 2, greater than 1, 2. Now 2 square, what we will get, applying in this formula, you will get as 2 square 4 minus 1, you will get 3, that is positive value, no negative value. So what you get construct from that, that is dA by A equals to some positive value of dV by V. They are not reacting a negative impact. So what the expression explains that if the area increases, the velocity will also increase, but the pressure, temperature, density will be having a reverse in nature. So first see the first one, supersonic nozzle. This shape is called as a divergent shape. When from the area gradually increases from this point to this point, when the area gradually increases, we call as a divergent section or divergent shape. So what happens in divergent? The area increasing gradually. So as per this supersonic, what will react? The velocity will also increase and the pressure, temperature and density will decrease. See, okay. Now go for the supersonic diffuser. This diffuser is called as a convergent shape or convergent section. What happens here? Here gradually the area decreases, So in this case, in supersonic, the area and the velocity are proportional to each other. So what will happen? When the area decreases, the velocity will also decrease, but the pressure, temperature, density will increase. And keep that in mind that velocity and the Mach number is proportional. How? Because as per from the definition of Mach number, that is Mach number equals to V by A, that is speed of light by the speed of sound. I hope this about the convergent divergent in supersonic and subsonic concept is clear. The first thing is that you have to remember this formula, okay, that is dA by A equals to dV by V and ma square minus 1. It is a very important conceptual formula, and how it has been derived already I have given a glance of it using two conditions or two assumption of equations, that is a continuity and momentum. Now comes a few glance of property relation for isentropic flow of ideal gas. Already in part 1, which the link is in the description below, I have explained moreover how we have derived this property relation for isentropic flow. If you need further reference, you can go down the description box and you can refer back to that isentropic flow derivation. I have given some tricks over there how you can memorize this formula, and so these are the basic formula and how it's relating. I have given how the stagnation, or in other ways we can remember like this structure, that is T by T naught equals to 1 plus gamma minus 1 by 2 m square minus 1. Okay, so now in front of this is an CD nozzle. Here from the reservoir the fluid is entering, so that's why we are considering as a stagnation properties where the velocity is 0. Now it is hitting on this point where it's called as throat. Throat is a critical because the Mach number becomes 1, and the properties of the critical properties we call as an in terms of T star, P star and rho star, that is temperature, pressure and density. And after the throat section we have a divergent section. So already I have discussed like if there is a divergent section, and why we are creating a divergent section, because we need to produce a very high velocity, and in supersonic when the area increases, what will happen? The velocity also increase, Mach number increases, but the pressure, temperature, density decreases. That is our criteria, so that's why we made it is a divergent section for a supersonic nozzle. So here you have to, this is a table of a critical pressure, temperature, density ratios for isentropic flow for some ideal gases. When the K value is 1.33, and for air we consider K equals to gamma, it is 1.4, and for monoatomic gas the gamma value is 1.667. So in air we can also consider it is a diatomic gas. So please focus on the rate border. So you have to remember this value. So first I am gonna tell you this formula, that is when you're from the previous slide you saw that the ratio is T by T naught equals to 1 plus gamma minus 1. So here comes the formula. So when you are substituting that Mach number is 1 and corresponding K value in the formula, you get this formula. And for air you have to remember this form, that is P star by P naught, it gives 0.528, that is at critical pressure ratios are the 0.528, and T star by T naught gives 0.833, rho star by rho naught equals to 0.634. Here comes the relation between the area and the Mach number relation. So it's very easy, you have to remember this formula. They ask a lot of questions in competitive or subjective types. It's a very important concept, but thing is like you might have a lot of confusions to remember this thing, whether it's K plus 1 by 2 K minus 1 or K minus 1 by 2 K plus 1. So I will tell a very easy way, like you can remember this thing like 2.4 by 0.8. I think I remember in this way, like how we got, we know usually we substitute that gamma value is 1.4. So when you plus with plus 1 you get 2.4, and the bottom we obviously gonna minus, if you remember, and just remember the total power you will get as 3. So when A by A star, this value A by A star plus this value equals to this value, and you get something power, the power comes 3. So if you have some manipulating skill, you can, it will be very easy for you to attempt for your competitive examination or in subjective questions also. Next comes isentropic flow through nozzle. You from here you have to remember the mass flow rate of a nozzle. You know what is a function of mass flow rate. Mass flow rate, when the entire mass flow rate remains constant throughout the section, that is we consider in terms of m dot, or its unit is kg per second. So you have to remember this formula, that is m dot equals to 0.6847 by root over RT P naught into S star. So here this value is only applicable for when the gamma value is 1.4 or when you are considering for air. You have, it's very important, what is P naught? P naught is a chamber pressure, S star is the area of a throat, R you know, T you know the temperature, and this, or if you otherwise you have to remember this formula. Well, I will come to this section. Now here I am going to explain how this shock behaves or how the property changes or back pressure changes within the entire system or entire CD nozzle. First I will, you just see a glance. Here the first case comes. Before first case, I am going to go in case A. What in the case A? See the figure in the right hand side, that is P naught is the chamber pressure, nozzle chamber pressure, and PA or dotted line you can see, that is the exit of a nozzle. So when the P naught and the exit pressure become same, so what happens in that case? That means PB by P naught will be 1, that is the ratio is 1, and that is ideally it's not possible, the Mach number will be completely 0. See the diagram below, you can see there will be no flow. When the Mach number is 0 means, that means no velocity, so no flow will form, and ideally it is not possible. Okay, then comes the case 1. In case 1 we are going to see when the P naught is slightly greater than PB and greater than PC. So it is, you can see in the figure and you can understand that PB, that means what happens, from the stagnation point and the exit pressure, it is decreasing a bit. So in that cases what happen, the mass flow rate is less than the choking flow. That means before it reaches the choking flow, but it has some motion of a fluid. That is, the fluid velocity increases first in the conversion section and reaches maximum at the throat section, but reaches some maximum, but the Mach number is not 1, but the Mach number is greater than 1. So let's see here what happens, or in other words we can also explain that when the PB is greater than P star, that is before it reaches a critical value. So what happens here? That means it lowers the back pressure. So here the Mach number is greater than 1, still it causes an subsonic flow. Now comes to the next case, when the PB is equals to PC. What happens here at some see the figure here, you can see that at some throat section what happens, it reaches the P star. What is P star? It reaches the critical value, and that point it reaches a Mach number 1. At the throat we reaches that M star equals to M equals to 1. That means at this condition we getting a maximum mass flow rate, and but there is a decrease in pressure. So you can see in the point which I have given a blocked section. Next comes the next one, when PC is greater than PB and greater than PE. You can see in the figure what happens in that cases, there is some causes of some normal shock wave. There is some formation of normal shock wave and acceleration, what it happens to the acceleration, and sudden come in stop. Next comes when PE is greater than PB. So you can see in the figure, it is completely an isentropic process. The region between the PC to PF, the entire process is isentropic, but what happens, there is some formation of normal shock wave. But when PB equals to PF, there is no shock wave within or outside the nozzle. Did you got my point? So that is, a PF is such a point in the divergence section, there is no formation of no shock wave within the or outside the nozzle. Next comes when PB is less than PF. So when there is a less than PF, there might be some expansion shock wave which might cross in the exit plane of a nozzle, that what it explained. But in case of PF, that is a point PF, there is outside or within, there is completely no shock wave, that we call as an optimum nozzle. That such kind of nozzle we call as optimum nozzle. Now by increasing the pressure and that means by gradually by decreasing the exit pressure, what we can configure it that at some point we causes some wake at the nozzle exit. That wake is nothing but the oblique shock wave, and it is which is completely a non-isentropic cause or non-isentropic process. So this all the I think I have explained around 7 to 8 important points. These 8 points are very important. If you have further inquiry, please you can comment in the comment section. I will be here to follow up your inquiry like that. Now comes to this shock behavior in nozzle. Now I am going to tell you how we are going to classify this shock behavior. So this shock behavior is mostly done by using this relation between the exit and the ambient pressure, or we can say ambient pressure is also known as a back pressure, which usually we say as PA equals to PB. So first we will see under expanded nozzle, then we will see over expanded nozzle. Most of you have a confusion between the under expanded nozzle and over expanded nozzle, but I will tell you a very easy trick how you can remember the under expanded and over expanded nozzle. Here First, what do you mean by under? Something less. And what is mean by over? Higher. So alphabetically the PA comes first and then comes E. So remember, so P first you write PA, then PE, then under means less and over means greater. So like how I feel this is a very easy trick to remember this under expansion and over expansion nozzle. Next comes an optimum nozzle. This is a case we have studied, that is case F. That is what happened when the ambient pressure and the exit pressure is same. So optimum nozzle. Now it's time for some MCQ. Condition of supersonic flow through throat with adiabatic condition is called the design pressure ratio of nozzle. True or false? See, what we have studied is it's completely an isentropic process. It doesn't follow any adiabatic process. This is a basic concept about it. So obviously this statement is false. That is option B. Next comes, for diatomic gas, critical pressure ratio is equal to. See, I have already said what is meant by diatomic gas. Air is a diatomic gas. You remember tabular column, and what is the formula? They ask about the pressure ratio. So you have to thorough with the formula, that is P by P naught equals to 1 plus gamma minus 1 by 2 m square by minus gamma by gamma minus 1. Now what is mean by critical pressure ratio? You might have forgotten the values. So what you can do is, if you have remember the formula, substitute the Mach number is 1, so and gamma value is 1.4, and you can get as 0.52828. So option A is the right answer. So which of the following relation is correct? So which of the following relation is correct? dA by A plus. So from here you can understand it's a relation between the area and velocity Mach number. So from here you can understand the recall the formula. From here you just write, you can see which formula, and option D is the right answer. Using the equation dA by A, dV by V and m square minus 1 for a nozzle, when Mach number is greater than 1, velocity in the nozzle will increase if the area of a nozzle. See, what is maybe m greater than 1? That means it is an supersonic flow. Next point is the velocity in the nozzle will increase. So we know in that case, recall the formula again, dA by A equals to dV by V m square minus 1. So what happens if the velocity increases, area also increases over here. So our right option is option B. Yeah. I hope this session was very useful for you guys. If you have further inquiry, please drop down to my comment box, or you can contact me in 9489224114ash@gmail.com. And thank you for watching this video, and don't forget to share this video with the needy fellows, teachers, junior, senior. Take care. Bye.